Did you hear about the chemistry major who asked the statistics major out on the date? She failed to reject him. And we will be talking about rejecting and failing to reject hypotheses as we do tests about a population proportion. So we're going to go ahead and look at this example with smoke detectors. A 1996 report from the U.S. Consumer Product Safety Commission claimed that at least 90% of all American homes have at least one smoke detector. A city's fire department runs a public safety campaign about the smoke detectors. So first of all, let me go ahead and just highlight some of the important information. This 90% is very important. That's probably our assumed value. And let's see, they're running a campaign on smoke detectors. They want to determine if the campaign has raised the local level above the 90% rate. So that amount of raising, that's important as well. Okay. He inspected 400 randomly selected homes, and it's important to know there were 400 and they were randomly selected, and finds that 376 have smoke detectors. So that's going to be part of our statistic calculation. Is this strong evidence that the local rate is higher than the national rate? So first of all, let's start with the state steps. Well, we want to test the null hypothesis that p equals 0.90. We have an alternate hypothesis that it's actually greater than 0.90. And the reason I chose greater is we said we're raising the local level. And I do need to tell you what the parameter is. P is the true proportion of homes in the city with a smoke detector. Also, let them know what alpha you're going to use if it's not given in the problem. Since it's not given here, we'll use the customary value of 0.05 or 5%. Now, we're going to move to the plan section where we check conditions. The conditions for a hypothesis test are the same as for a confidence interval. So now when we're using the normal approximation for proportions, we're going to, instead of using an interval, we're going to use a one sample z test for p, also called a one prop z test on the calculator. We also need to know that the data comes from a random sample, or we're told that the sample is representative. Remember that the whole reason we do randomization is to get a representative sample or and to get rid of bias. Now, the 10% condition is important because when we're sampling without replacement, which is most of the time, we need the sample size to be less than 10%. Why is that? Well, we make the assumption that the proportion stays the same, and if we take more than 10%, our proportion is starting to change. Secondly, our calculation for standard deviation will now be messed up, so we're going to be a little bit off on the calculations. So you need to verify that your sample size is less than 10% of the pop, or state that your population must be more than 10 times the sample size. Either one of those should work. Large counts condition, which we did before, n times p, where p is our hypothesized value, must be greater than or equal to 10. I know it feels like we have a lot of 10s. And n times 1 minus p, sometimes you'll hear me call that q, that also has to be greater than or equal to 10. Why is that again? Well, if I have a really low p, then my probability, the distribution will be skewed because I'm going towards the end. And so instead of looking like a nice normal symmetric, I'm cutting off the tail and it's sort of squishing things on the end. And that's whether either end of the spectrum, whether you have a high P or a low P. So let's go ahead and look at these smoke detectors. We're going to go ahead and do plan now. So let's name our test method, which is the one sample z test for P. And checking our conditions, they told us that it was random. So it's given that the homes were randomly selected. 10%. Did we take over 10% of the population? Well, it's reasonable to assume that the town has more than 4,000 homes. So it's reasonable to assume that 400 is less than 10% of the homes in the city. Then on large counts, we're going to take that 90% and multiply it by our sample size, and we get 360 for the high P, and for the low P, which the 1 minus P, which you see I sometimes call Q, we get 40. Both of those are bigger than 10, so we're fine. So how do we actually do a one sample z test? Well, if conditions are met, we're going to use the normal distribution. That's why we had the conditions. And we're going to calculate a probability, also known as the p-value. For a one-sample z-test, a standardized test statistic is z, and this is from your math chart right up here, but I'm going to fill it in with values particular to proportions. Our statistic in this case is actually going to be p-hat, and the parameters p-naught are hypothesized value. So you're going to go p-hat minus p-naught over your standard deviation for the proportion. Now we can get that from the formula chart, and we ran into that when we were doing the confidence intervals as well. It's still the square root of p times 1 minus p over n. So now you're going to use your alternate hypothesis to determine how to shade the normal distribution to show what p-value you're seeking. If your alternate is p is less than your hypothesized value, mark Z for your sample and shade left of the Z value. So I'm kind of doing Z's on this version of notes right now, and it'll make it easier for that middle part. So we are looking at the probability that Z is less than the number we got for our test statistic, given that the null is true. This is called a left-sided test. It can also be called a one-sided test. We then have the two-sided test, which is P is just not equal to P naught. So we mark the Z for our sample and the negative of Z. So we're going to have both sides, and we shade both tails. So we have 0 in the center, and then we'll have two symmetric Z's and shade both those tails. So we have the probability that Z is not equal to the number. You can ignore that blank there, given that the null is true. And this is a two-sided test. And finally, we're going to look at the alternate hypothesis that P is greater than our hypothesized value. So we're going to mark Z for the sample and shade to the right of the Z. So here you go. There's your 0, there's your Z, and shade to the right. We would say the probability that Z is given greater than our test statistic, given that the null is true. And again, this is a right-sided test, or also known as a one-sided test. Recall, here I'm using Z values. So my normal CDF will always be my left boundary and my right boundary. Those are going to depend on what I'm shading. If I'm doing this middle one here, I'm actually going to calculate just one of these and then double it. So it could be in this one, my left boundary is negative infinity to Z. This one, I could use negative infinity to Z, or I can use Z to infinity, where I have the positive value. Just make sure to double it because I'm only doing half of the test. And finally, this one, I would have my lower boundary would be Z, and my upper boundary would be infinity. Since I have Z scores in this example, the mean for Z is always 0. See how I have a 0 in the center? And standard deviation is 1 because Z's are counted in units of 1 standard deviation. The p-value that we get from this calculation represents the probability of getting the result you obtain, whatever you saw, given that the null hypothesis is true. So let's go ahead and do the do part and calculate our p-value. So we know the proportion is 0.90. We calculate the standard deviation using the formula, and this is our model. The mean of 0.90 and a standard deviation of 0.015. If I were to fill in the picture here, I know that 68%, 95%, and 99.7% would fall there. So that gives me a nice picture of the model. Now, normally you don't have to do that. So let's go ahead and actually calculate the p-value. So my p-hat is 0.94. And my test statistic is going to be p-hat minus p-naught over the standard deviation. 0.94 minus 0.9 over 0.015, which is 2.667. So I want the probability that it's that much or higher. So 2.667 is the low value on my normal CDF, and infinity is the high value. And if I calculate it, it's a very low value, 0.0038. And you can see here on this top graph, this is in Z-scores. And on this bottom graph, it actually shows the X values. So now that I have my p-value, what kind of conclusion can I make? Well, because our p-value of 0.0038 is less than 0.05, we reject the null that the true proportion of homes in the city with fire alarms is 0.90. This has given us convincing evidence that the true proportion of homes that have fire alarms is actually greater than 0.90. So now let's go ahead and look at significance levels for one-sided and two-sided tests. You do have to treat them differently. A one-sided test is going to put all your alpha just on one side. A two-sided test, let's say you want to be, it's almost like a confidence interval. If you want to be 95% sure, you have to split that extra 5% on each side. So if my alpha is 0.05, for a one-sided test, my z value is 1.645, where it's the cutoff where I decide. If it's a two-sided test, it's actually 1.96. This may look a little familiar from when we were calculating critical values for confidence intervals. Let's go ahead and look at 0.01. Now you can see I have an even higher z, and it's also true for a two-sided. In fact, it's even higher than for a one-sided. And then for 0.001, you can see my z has gone all the way up past 3. And for a two-sided, it's almost a 3.3. So what are the main differences between intervals and hypothesis tests? Well, confidence intervals are really giving me plausible values. They're actually estimating. While tests check plausibility of a value that you're already given. Now, an advantage, we can approximate a parameter using the confidence interval. Can't really do that with a hypothesis test. But remember, if you decide to use a confidence interval to test it, hopefully you're doing a two-sided test, all right? It's a little trickier to do a one-sided test with a two-sided confidence interval. You need to make some adjustments, and you probably don't want to do that. So don't forget that confidence intervals are two-sided. So when using a confidence interval for a two-sided hypothesis test, here's how you can deal with it. It's pretty straightforward. You take 100% minus your C%, and it's all good. We're fine. If you want to make that adjustment and use a confidence interval, then you actually have to use half as much for your alpha. In other words, you're going to make it stretch out a little bit so that you can use it for a one-sided test. So your alpha is going to be just that 1/2. You know how on the two-sided, you have the two red sections. If you're doing it one-sided, you only have the one red section. So you have the half outside the confidence interval. So let's go ahead and look at a confidence interval for the sex of firstborn children. And the interval for males was 0.5091 to 0.5253. And this is with a 99% confidence. Here are two ways you could interpret it correctly. One is, and this is the easiest, we are 99% confident that between 0.5091 and 0.5253 of firstborn children are male. If this survey were conducted many times, and here we're talking more about the confidence level, then about 99% of the resulting confidence intervals would contain the true proportion of the firstborn children who are male. So the top one is really how we interpret an interval, and the second one is for interpreting a level. Now, you really don't want to say these. The percentage of all firstborn children who will be male is between 0.5091 and 0.5253. You're only 99% confident. You don't know that that's actually going to happen. There is a 0.99 probability that the true percentage of male firstborn children is between those two numbers. Technically, the true percentage is already a number. It's not hopping around and uncertain if it's going to be in your interval or not. It is where it is. If this survey were conducted many times, then 99% of the sample proportions would be in the interval. No, we don't say that other sample intervals are going to match our interval. All right? So let's go ahead and revisit alpha, beta, and now we're going to introduce something new called power. So for me, the easiest way to keep type 1 and type 2 straight is type 1 happens when Type 1 happens when H0 is really true. So this is my first hypothesis, my null. When the first is really true, then it's possible I can make a type 1 error. Well, how do I make a type 1 error? Well, I think that it's actually not false. And which samples would cause us to say that we have evidence against it? Well, that would be the ones that are really far away in this level where we say, oh, if it's in this 0.05, we reject it. So alpha is the probability of making that type 1 error. Now, a type 2 error occurs when the alternate is really true and the null, the first one, is really false. Beta is the percent of samples. So why do I have one picture up here and two down here? So if H0 is true, then we're using the correct model to make our predictions, all right? So we actually have it centered around the hypothesized value, and that is what our population looks like. If our hypothesized population is different from our actual population, then I'm going to have this distribution that I'm using to do the test, but in reality, my distribution looks like the bottom one. Okay, so beta is the probability of me not knowing that I have a different distribution. So all these samples in the real distribution would give me a value that's okay with the null, all right? I have to be further away than this line here to reject the null. So these are all the samples that could lead to a mistake, whereas these would help me realize and reject the null. So again, type 1 is when the null is true, the first hypothesis. Type 2 is when the second hypothesis, the alternate, is actually true. So again, alpha is the probability of making a type 1 error. Beta is the probability of making a type 2 error. So power is 1 minus beta. Notice that these two add up to 1. The probability of correctly rejecting H0 given that H0 is false. Type 2 error, that we said, is beta. And type 1 error is alpha. So we agree on what level of errors we're willing to make. Now, most times, you're not going to be calculating power. But I think you're going to understand it a little better if we can actually do an example where it is possible to calculate power. You can calculate power if you actually know the true value, which most times we don't. But I'm going to make up an example where we know the actual percentage and the hypothesized percentage. So the true proportion of seniors who will go to prom this year is 20%. The prom committee believes that 30% of seniors will go to prom. They survey 100 seniors to make sure that the true proportion is not less than 30%. So our null is, what is the prom committee assuming? They're assuming 30%. They're worried that it might be less than 30%. That's your alternate. So this is what they think the population looks like, all right? And what value, if they sampled, in this case, they did 100 seniors, how many seniors, how low a value must they get to say, oh, this isn't really true? They would actually have to get an alpha less than 0.05 or a p-value less than 0.05. And so that would be an x value of 22 or a z of negative 1.645. So here I was using a binomial distribution to look at the hypothesized distribution. So any x of 22 or lower would cause us to reject. Okay, so we know alpha. Now, let's go to the actual distribution, the true distribution. So we know that we're going to reject if x is 22 or lower. So let's look at the true distribution and see what percentage of samples would give us a value of 22 or lower. Well, in this case, it's 73, almost 74%. Okay, so 74% of the samples would give us 22 or lower. So 74% of the time, we would reject the null and choose what we're supposed to have evidence for, which is the alternate. So alpha is something we picked, and that's 0.05. The power is 74%, and beta is 1 minus that number, or 0.26. How do we interpret it? Well, if the true proportion of seniors who are going to the prom is actually 0.20, then there's a 74% chance probability that the committee will find convincing evidence for the alternate. So it's the probability of finding evidence for the alternate. Let's go ahead and revisit this now with a sample size of 200. Let's say they say, oh, we want to be a little bit more sure, all right? Because 74% of the time they'll be able to tell, but that's still a little low. So first of all, here's our hypothesized distribution. They think 30% of seniors are going to prom, so 60 out of 200. And we know the real truth is that 20 out of 200, 40 out of 200 will go. So what value do we need to get to reject the false hypothesis, the null? Well, I have to get less than 0.05 because we're using an alpha of 0.05. And I played with this and I found out, oh, if x is 46 or less, then I will end up rejecting the null. Okay, now let's go to the real distribution and find out what's the probability of me getting 46 or less on the real distribution. And it's actually 93.1%. So the x value of 48, I said 46, 48 or lower will get us a p-value lower than 0.05. All right, so that value is the probability we will reject it. With the sample sizes of 200, if the true proportion of seniors who are going to prom is 0.20, then there's a 93% probability that the committee will find convincing evidence that the true proportion is less than 30%. Now, so my alpha, let's go ahead and recap these. My alpha is 0.05. My power we found out was 0.93. And beta is 0.07. These two always add up to 1. What effect did increasing the sample size have on alpha, power, and beta? It actually has no impact whatsoever on the alpha because that's the number we're picking. Usually it's the 0.05. Power, it did have a chance. It actually increased the power. Remember, it was more like 74%. Now it's 93%. Well, if power goes up, beta goes down, and our beta decreases. So now let's look at changing alpha from 0.05 to 0.10. We're going to keep the 200 sample size and see what happens when we change alpha. Well, what really happens is that now I can have a bigger chunk of the hypothesized values aren't going to cause me to reject because you're going to have if I have a value less than so I'm going to have a bigger chunk of values causing me to reject. All right, so now my x has to be less than or equal to 51. So any x less than or equal to 51 will get me a p-value of 0.10 or less. So that's kind of broad in this section here. Then when I go over here and say, okay, if x is how much of the true population is less than or equal to 51, well, it's 97%. So power, almost 98 actually. So power increased from 0.93 to 0.98 and beta decreased from 0.07 to 0.02. Again, remember these two always add up to 1. So high power is good, low alpha and beta is good as well because alpha and beta are probabilities of error. Power is the probability to detect a difference. So if someone wants to increase the power of a test, what would you recommend? The easiest thing to do is to increase the sample size. Your other option is to increase alpha, but that means that increases your probability of a type 1 error. So you can do either one of those or a combination of the two. Finally, I want to give you a new mnemonic device to kind of remember all the pieces that go together. I know we've been doing step, plan, do, and conclude, but this device, we call it phantoms, will also help you do those steps. So P stands for state your parameter. H is state your hypotheses. A is list any assumptions and also conditions. N is name the test. So the N is really coming from naming. T is find your test statistic. O is obtain your p-value. M is you're going to make a decision to reject or fail to reject. And S is state a conclusion. The S comes from state in the context of the problem. So we'll go through one more example, but now we're going to use the phantom structure to see if that helps you remember to do all the steps. Let's practice using phantoms on another example. There's supposed to be 20% orange M&Ms. So suppose a sample of 122 randomly selected M&Ms from the production line has only 21 orange ones. Does this contradict the 20% claim? So P, we're going to use phantoms. P is your parameter, which is P equals the true proportion of orange M&Ms. H is your hypotheses. So that P, we're going to assume that P is 20% or 0.20. And since we just want to contradict the claim, we're not really saying greater than or less than. We're just going to go with the not equals form. So this is a two-sided test. I'm going to go ahead and list the alpha here because I always like to do it before I get into other things. And that is going to be 0.05 because we weren't told anything else and there's no reason to assume otherwise. In theory, you could give me a different alpha and I would have to do all the math to go with your alpha. Actually, luckily, it's pretty easy. It comes in at the end. Now let's check our assumptions, and that means conditions as well. Is it random? Well, it's given in the sample that it's random. Large counts. Use your hypothesized value, not your sample, to calculate n times p. We get 24.4. And n times q, the 1 minus p, we get 97.6. Both of those are greater than 10, so we have met the large counts condition. And why do we need it again? To make sure that our distribution is not skewed. We needed the random to make sure it was representative, and the large counts helps to make sure that we have a nice symmetric distribution. 10% condition. It's pretty reasonable to assume that they're producing more than 1,220 M&Ms. So it is reasonable to assume that 122 is less than 10% of the total population. Now we hit N on phantoms, which is name the test. We're going to do a one sample z-test for proportion, and then T, which is the test statistic. So I'm going to go ahead and calculate p hat from my sample, which is 21 over 122, which is 0.172. Now there's a really easy mistake if you do it in this order. If you do p hat and then you're like, oh, let me do sigma p hat. Well, technically we're supposed to use the hypothesized value here. Don't use the 0.172. That's tempting. And the thing is when you're doing confidence intervals, you don't have a hypothesized value, right? So you've got to use the 0.172. But on a test, we're testing this p is 0.20. So that's what we have to use. So make sure you use the hypothesized value here, and there's your standard deviation. Then we calculate our test statistic, which is our statistic from the sample minus our parameter over the standard deviation for the parameter. And we get a z-score of negative 0.778. So now we're going to obtain the p-value. And let me draw my normal distribution. I have my test statistic, which is negative 0.778. And I'm going to shade to the left of it because I'm getting away from the parameter. But wait a second. This is a two-sided test. That means I also have to shade the negative of that z, which would be positive 0.778, and shade the other tail. Now you can see already that this is a pretty high p-value, but let's go ahead and calculate it. It's kind of hard to do two of those at once, so we'll just do half of one side. We'll do half of it, which is just one side. So half of my p-value will be a normal CDF where my lower is negative infinity, upper is negative 0.778, with a mean of 0 and an SD of 1 because I'm using z-scores instead of x values. And I get 0.218. Now I'm going to actually double that to get my actual p-value and to represent this other half that's on the other side. The next step is to make a decision. Well, I have a p-value of 0.436. It doesn't seem that uncommon to be that far away from the parameter for orange M&Ms. So we're going to say, because our p-value of 0.436 is greater than the alpha of 0.05, we fail to reject H0 that the true proportion of orange M&Ms is 0.20. And we can say that there is insufficient evidence that the true proportion of M&Ms is not 0.20. And hopefully there tends to be a structure on this conclusion. P-value, is it bigger or smaller? Reject or fail to reject. Second statement, evidence, sufficient evidence or insufficient evidence for the alternative, just to kind of remind you about that.